All right, so we're in section 3.2 today. And we're going to talk about logarithmic functions. So yesterday we talked about exponential functions, and so we talked about exponential functions today, and we said exponential functions had the form y equals a to the x for some value of a and for our variable x. And if we sketch a quick graph of an exponential function, the graph is going to look something like that. So all of our exponential functions look more or less like that if a is greater than 1. So our exponential function is going to look something like that. Well, does this graph pass the vertical line test? Yes? This graph passes the vertical line test. So this represents a function. Does it pass the horizontal line test? Does a horizontal line ever cross the graph in two places? No. So the graph passes the vertical line test and the horizontal line test. Do you remember? Anybody remember what that tells us about a function? If it passes, it has an inverse. Very nice. So exponential functions have an inverse. So exponential function have an inverse function. And another name for a function that has an inverse function is that it is a one-to-one function. And that means for every x value we get exactly one y value. So our exponential function has an inverse function. We call the inverse function the logarithmic function. So our inverse function is and we say f of x equals the log base a of x. So this is our logarithmic function. This is our inverse function for our exponential function. And we're saying that x has to be greater than 0. So x is positive. And we're saying that a is greater than 0. And a doesn't equal 1. So this is our logarithmic function. We call this the logarithmic function with base a. So the number down here is our base for our logarithmic function, just like the number here is the base for our exponential function. We call this a logarithmic function with base a. And what this means, because these two functions are inverses of each other, we're going to say that y equals log base a of x if and only if and only if a to the y equals x. So these two things, these two equations, mean exactly the same thing. If log to the base a of x equals y, then a to the y equals x. It's extremely important that we remember this relationship between exponential functions and logarithmic functions. We call this form of the equation, we call this the logarithmic form. And we call this the exponential form. They are telling us exactly the same thing. These two tell us exactly the same thing. They're the exact same relationship between x and y. Now, I know when you worked with logarithmic functions in the past, a lot of teachers have different tricks for how to remember to switch from logarithmic form to exponential form and back, talking about rolling logs and that kind of thing. That works. That's fine. The way I think about this is we can think of this as, we can think of log as the power of. The power of a that gives us x. The power of a that gives us x is y. So a to the y equals x. So that's how we think of the relationship between logarithmic functions and exponential functions. So the power of, or the exponent on. The exponent on a that gives x is y. So a to the y equals x. So what I want to do is do a little practice switching back and forth between logarithmic form and exponential form. So let's look at a couple of examples. Any questions before we move on? Okay. So, if we have log the base 2 of 8 equals 3. So these are our logarithmic form. Guys. And we want to switch these to exponential form. Whoops. So our logarithmic form is log base 2 of 8 equals 3. How would we write that? How are we going to switch that to exponential form? 2 to the third equals 8. So these two mean exactly the same thing. If I have log base 2 of 0.25 equals negative 2, how am I going to write that in exponential form? 2 to the negative 2 equals 0.25. How about log base 3 of 81 equals 4. 3 to the fourth equals 81. So I can think of these as the power on, or the exponent on 2 that gives me 8 is 3. So 2 to the third equals 8. The exponent on 2 that gives me 0.25 is negative 2. 2 to the negative 2 is 0.25. The exponent on 3 that gives me 81 is 4. 3 to the fourth equals 81. Let's look at a couple of more. So what if I just wanted to evaluate? So if we were just saying evaluate. So if I say log base 10 of, or let me start with this, log base 16, well, I don't want to do that one. We'll do log base 10 of 1 over 1,000. So I want to evaluate this. So what exponent on 10 gives me 1/10,000? What power do I have to raise 10 to get 1 over 10,000? So let's go the other way. Let's think without without the fraction. What power on 10 gives me 1,000? 10 to the second power is what? 100. So 10 to the
Well, the denominator is 1,000.
right. So that's what I'm saying. 10 to the third is 1,000. So what's going to give me 1 over 1,000?
1/3.
10 to the negative 3. So the log base 10 of 1 over 1,000 is negative 3 because 10 to the negative 3 equals 1 over 1,000. So if we were to evaluate, when we're evaluating, it's at the question is asking us, what power do we have to raise our base to get this answer? So 10 to the negative 3 is 1 over 1,000. How would I rewrite log to the base 16 of 8 equals 3/4? How would I put that in exponential form? (16 to the 3/4 equals 8). So if I wanted to write this in exponential form, this is all I would have to write. 16 to the 3/4 equals 8. This one would be, I'd leave it like this. Let's look at a few more. I just want to do some more practice with these types of problems. We want to rewrite in logarithmic form. So now we're going to switch to logarithmic form. 8 squared equals 64. How would I write that in logarithmic form? You have an idea, Dane? All right, guys, let's stop talking. What's our base? Log base 8 of 64 equals 2. Perfect. So our base of the logarithm is the same as the base of our exponential function. So this would be log base 8 equals 64. Exponential form, logarithmic form. How about 9 to the 3/2 equals 27? How would I write that in logarithmic form? Log base 9 of 27 equals 3/2. All right, this one is similar to the one we just did. We're kind of going the other direction. 10 to the minus third equals 0.001. How would I write that in logarithmic form? What do you think, Erica? Log to the base.
Log to the base. Log to the base.
10. Our base of our logarithm is the same as our base of our exponent. Log to the base 10 of 0.001 equals negative 3. All right, a little more challenging one. U to the V equals W. How am I going to write this in logarithmic form? Log base U of W equals V. So that's our logarithmic form. So a big part of what we're going to do with our homework and a big part of what we're going to do when we solve problems with exponential and logarithmic functions is being able to switch back and forth between exponential form and logarithmic form. All right, let me talk about some properties, some important properties of the logarithmic function. So we're going to talk about the common logarithmic function. So a couple of bases for logarithmic functions and for exponential functions show up so frequently that we come up with special symbols for them. One of them is log base 10. Log base 10 is what we call the common logarithmic function. Common. And this is normally when we have base 10, we don't write the base. We just say log. And your calculator has a log button. That's log base 10. So base 10 is our common base. Base 10 is called our common base because we use base 10 so much. So base 10 is our common. So if you just see log x, that means base 10. If you don't have a base on your log, then you assume that it's base 10. So that's one of our special bases. I'll talk about another special base in just a minute. But I want to write some properties of the logarithmic function. So the properties of any logarithmic function. And these again are going to be important for the types of problems that we're going to solve using exponential and logarithmic functions. We have several of them. Log to the base a, any base, of 1 equals 0. This is for any base. And that is because a to the 0 always equals 1, no matter what. Our second property, log the base a of a equals 1. And if we rewrite this in exponential form, that's because a to the 1 always equals a. So these mean the same thing. Because the logarithmic function and exponential function are inverses, log to the base a of a to the x equals x. So if our bases are the same, the logarithmic function and the exponential function essentially undo each other. And the opposite is also true. A raised to the log base a of x power equals x. The logarithmic function, if they have the same base, the logarithmic function and the exponential function basically undo each other. And these are because they're inverse functions. And our last property is that if log the base a of x equals log the base a of y, then x equals y. If our bases are the same and our logarithms equal each other, then the numbers inside the logarithms equal each other. So this works for any base and for any x and y. So these four properties are going to be important for the types of problems that we're going to solve with exponential and logarithmic functions. So any questions on these properties? I just want to do a few examples with these. So if we want to solve the equation. So for this one we have log base 5 of x equals log base 5 of 8. What are the properties of logarithms tell us here that x has to equal? X has to equal 8. We have the same basis. Our logarithms are the same, so x equals 8. Second example, log base 5 of 1 equals x. So for this one, we're going to think, what power do I have to raise 5 to get 1? 0. 5 to the 0 equals 1. So that means x equals 0. The power that I have to raise 5 to get 1 is 0. So x has to be 0. And if you have other ways of remembering how to do logarithms, I know a lot of people talk, I hear students talking about rolling the log. I never learned it that way. If that helps you remember, that's fine. I always just think about it as, what power do I have to raise 5 to get this number? Questions on these examples? All right, one last thing to talk about today. Natural logarithms. So the natural logarithmic function. So our common logarithmic function is base 10. Natural logarithmic function is base e. And we talked a little bit about the number e yesterday. So for the natural logarithmic function, base e shows up a lot, so we give it a special symbol. We write for our natural logarithmic function, f of x equals ln x. ln stands for natural log. And this is the same as log base e of x. Natural log ln means log base e. And the natural log function is the inverse of e to the x. So our inverse function is e to the x and natural log of x. Those are our inverse functions for the natural logarithmic function. So anytime you see this ln, that just means base e. And your calculator has an ln button, and your calculator also has an e to the x button. And we're just using base e, where the log button and the 10 to the x button is using base 10. So we're just using a different base here. So let's look at a few examples using natural logs, and then we're done for today. Let's say we have natural log of e to the 5 equals what? What power do we have to raise e to get e to the 5th? What's the exponent on e that gives me e to the 5th? 5. I have to raise e to the 5th power to get e to the 5th. Because e to the 5 equals e to the 5. So if I thought about this as, I'm going to write this isn't how we usually write this. log base e of e to the fifth, I can rewrite that as e to the fifth equals e to the fifth. So my exponent has to be 5. How about e to the natural log of 3? What is that going to equal? Natural log function and the exponential function are inverse functions of each other. So what does what do e and natural log do to each other, essentially? Cancel out. They undo each other. So if I cancel these two out, what am I left with? 3. So my answer is going to be 3. The exponential function and the natural log function are inverses of each other, so basically they undo each other. How about the natural log of 1 over e squared? What is the exponent on e that gives me 1 over e squared? Someone said it? -2. Because 1 over e squared equals e to the minus 2. So my exponent on e is -2. So the exponent on e that gives me 1 over e squared is -2. Let's do a couple more of these to practice. How are we going to write? I want to write these in exponential form. So write this one in exponential form. The natural log of 4 equals 1.386. I'm going to write that in exponential form. Can you help us out, Shannon? How would I write this in exponential form? What's my base for the natural log function? E. So what's my exponent? E raised to what power gives me 4. 1.386 equals 4. So this is exactly like we did with the other bases. Just here my base is e. E to the 1.386 equals 4. This last example, I want to write in logarithmic form. So I have the natural log of 1.6487 equals 1/2. Actually, I'm sorry, I wrote it backwards. I want to write this in exponential form. So how would I write this in exponential form? What's my base for the natural log function? E. E to the, what's my exponent? 1/2. So this in exponential form, e to the 1/2 power equals 1.6487. So these are exactly like we did on the other examples, just my base is e. And our homework tonight is going to be a lot of practice with logarithmic form and exponential form and kind of switching back and forth. Any questions before we stop? Okay. Tomorrow we will talk about graphing logarithmic functions, and we'll do some more practice with these, with switching forms. So our homework. I'm going to shorten this because I only did part of what we're going to talk about, 2 on 6. number 1 through 31 off.